Welcome back for part 2 of our lecture series on using the Raspberry Pi to build your own smart doorbell. Quick recap of lecture 1, we were going to use our Raspberry Pi Plus camera to create our own smart doorbell system. So in lecture 1 of this series, we set up our Raspberry Pi and we created a alignment image to confirm that the setup of the Pi was correct, that the camera was aligned correctly. We created a function mask image that took that alignment image and masked the image spatially such that we were only looking at the user-defined area where someone or something would enter. We then resized that image, grayscaled it, and blurred it. And so we made it through this process in lecture 1 of this lecture series. We'll continue here in lecture 2 with the development process. We'll now record 2 images, we'll mask the images, and then we'll write the code to create the detection algorithm that will allow the Pi to decide if someone or something has entered the user-defined area, and then continue on with the detection process and notifying the user. Here is sample data to give you an idea of where we're headed. At left is the first and second image from a sample data set, and that user-defined area would be the same area that was masked in the first lecture. So the change here was sufficient to reach a threshold by which the smart doorbell algorithm said, okay, let's go ahead and record. In this case, I think it was a 30-second video. And so the result is shown at right, and that's the video file that was uploaded to Dropbox in this case, and the images at the left were uploaded and emailed via Gmail to the user being me. Here's another data set, right, where the Amazon worker is walking up from her van. She crosses into this user-defined area. There's sufficient change such that the detection algorithm says, okay, someone or something has entered the user-defined area, and then it kicks off this detection algorithm. And so depending on the image size here, this is at 640 by 480. These videos were 1280 by 720. Regardless of your image size, if your mask is set up accordingly, you can define when something has entered that user-defined area and continue with the detection algorithm. Let's jump back into the code then and continue designing our smart doorbell. So here I have VNC Viewer. I'm going to go ahead and connect to this Raspberry Pi, and I have a terminal window open up here. So first thing I'm going to do is I'm going to create a directory on this Pi such that I can keep all of my files organized relevant to this particular exercise. So we'll go ahead and say sudo for superuser_do. This will be make directory, and I'm going to call this smart doorbell. And we'll hit enter, and I'll go ahead and change directories into this smart doorbell, right? So SM, I'll just tab over, it'll complete. And if we ls for list, we'll see there's nothing inside of this directory just yet. Let's begin then by going ahead and moving that file that we were creating, this Python script that we were creating in lecture 1. We'll go ahead and move that over using an FTP client here to this new directory. So here's smart doorbell directory. And now if I go back into this directory in ls, we'll see nothing pops up, but that's because I just copied that over with FTP. So let's just cd out of that and cd back into that directory, and there we go. There is our Python script inside of this smart doorbell folder. Let's go ahead and just clear this screen and let's continue. So the first thing we're going to do is create a new alignment image just to verify that everything is still aligned. To perform that operation, let's run a raspistill again. That'll be -w, and I'll set the width at 1280 pixels. We'll give it a -h. We'll set the height at 720. Let's vertical flip it and let's horizontal flip it, and then we'll open. We'll just call this testpic.jpg for the moment, and go ahead and run that script. Now if I ls, I'll see there's my test pic. Let's go ahead and open that file, xdg open test. We'll just tab over and it should go ahead and open up that file. Okay, good. So there is my alignment image. Just recorded that. I'm connected to this Pi I called old Pi. It's an older Pi that I have here at home, connected to that Pi through the Wi-Fi here in the house. So very good. So let's get out of there. And from here, let's go ahead and start to code up this detection algorithm. Let's begin by opening up this smart doorbell masking file. So I'll run a sudo nano and I'll tab over and open up this file here. I'll be using the same Python packages in this lecture. So use NumPy, CV2, and imutils. And you'll notice the code is all the same from lecture 1. So we're basically going to take advantage of that and we'll reuse this code. Now, because of some of the procedures that we want to follow, I also want to return not just gray here, but I also want to return masked. We'll see why a little bit later. But otherwise, we're going to use this mask image function exactly as we wrote it in lecture 1. Let's go ahead and we'll just blow out all of this material. And let's continue then with our detection algorithm. So to recap, the idea is that we are continuously recording a first and second image. We are masking those images, blurring, grayscaling those images, right? And then comparing those images, and we're looking for change detection. It's a relatively simple algorithm for this lecture series. Could certainly be improved. There's more elegant ways of doing this. But as a first cut, we're going to do a simple change detection algorithm. And so we want to get into a loop where we're constantly looping through and constantly looking at these two images. So let's go ahead. I'm going to define here a counter, and I'll call it counter equals 0. And we'll just say this will be a counter variable for analysis, right? That'll just give us kind of an idea of, well, hey, how many times through the loop has it been since we last detected something? And then I'll get into this while true loop, right? This will basically just run forever. We'll come over, we'll tab over, I'll say counter equals counter plus 1. We could also say counter plus equals 1. That would be fine. And let's go ahead and print then this information to the screen. Now, I'll tell you on this Pi, because it's an older Raspberry Pi, I'm still running Python 2. All the code should be the same for Python 3 except these print statements. So if you recall, the older Python 2 print statement did not have any parentheses around it. So let's go ahead and give ourselves a new line. I'll print, let's call this times through loop since starting. We'll say comma counter and then comma, give ourselves a couple dashes again just for aesthetics. And we'll go ahead and give ourselves a new line here as well. I think I had 5 dashes, 4 dashes. Doesn't matter, it'll just be for aesthetic purposes. And then let's go ahead and give ourselves another new line, and that'll be kind of nice. So each time through the loop, it will tell us, okay, here's a number of times that we've been looping through, a number of times that we've compared first and second images since we began this process. Now I do want to go back up here and import one more package while I'm at it, right? So go up here, let's import the time package. And we'll do this because we'll just put some time.sleeps into the functionality, and that will be nice for timing and debugging. So for kicks, let's go ahead and put a time.sleep. Let's sleep it for 1 second, and then we'll control X, yes, enter, and let's go ahead and run that. So for me, it'll be Python smart doorbell masking, and I'll hit enter. You see here I have an error that is no module named CV2. This is an older Pi, and so if you have a virtual environment on your Pi, you'll want to make sure that you source your profile and then work on that environment. If you're using a Raspberry Pi just out of the box without virtual environments, you obviously won't need to perform this step. But let's go ahead and run that script again. And you'll see now we're counting through the loop. This will continue on essentially forever. And I have that 1 second delay to kind of indicate, okay, time through loop, time through loop, time through loop. Let's go ahead and control C. We'll break out of that. And I'll just go ahead and clear the screen. So we want to compare one image to the next, and we want to say, did someone or something enter this user-defined area? We want to look for sufficient change. And of course, we have to set a threshold on that change. What does that mean? So the question is, the first question should be, how are we going to collect these two images? And there's a variety of ways to tackle this in Python or Python with OpenCV. For this exercise, we're going to take advantage of Raspistill, and we're going to take advantage of the fact that Raspistill has a time-lapse functionality. So if we take a look at the documentation on the time-lapse functionality, you'll see that Raspistill has this built-in time-lapse mode, right? So if we run a Raspistill-T for time, this will be 30,000 milliseconds. And we can also describe then the time-lapse-TL. That'll be the number of seconds or milliseconds between images. And then we can open up those images. And if we want, we can put sort of an incremental number here to indicate, the order of the images. We're going to do that with basically a test 0 and test 1, or you could do it with 1 and 2, etc. But we'll use this Raspistill functionality. It's kind of nice because you can define how quickly you want to take one image to the next. And that's something to consider when you're designing one of these systems, right? You have to say, how quickly should the images be recorded such that I can detect change, but you don't want it to be too quick. If you went to the extreme of milliseconds or microseconds, right, you wouldn't have enough change occurring between those images. So there's some trades to be had here in terms of the timing of that image recording process. So back in our terminal window, let's go ahead and just hit the up button. We'll go back to editing this nano file here, and we'll go down to, for me, it's Control V, go down the page each time. So let's go ahead, after times through loop, we'll tab over, and let's take a first and second image to compare, okay? So I'm going to use the OS functionality in Linux and also available here in Raspberry Pi. So if I go up, I'll need to import again, import the OS package, some really nice functionality that you can use with the OS package. And I'll right now this command, we'll say command equals Raspistill. Let's give it a backslash width of 1280, a dash width of 1280, a dash height of 720. We'll vertical flip it, we'll horizontal flip it. Let's go ahead and for our purposes here, let's give it a total time of 1,000 milliseconds or 1 second. And the time lapse will be also 1,000 milliseconds or 1 second. Let's go ahead and open test, and we will essentially just give this a 0D JPG. I really just want to record basically test 0 and test 1 because I want two images to compare. And so if I have the total time at 1 second, right, and the time lapse at 1 second, it's going to record the 0 and the first test.jpg, and then it's going to break out of that command. So that's really all that I want to do in this line. That's the functionality that I want to implement. And to run that, we'll do an os.system, and we'll put command in there. And then let's just tell the user, hey, we did something here. So we'll go over and say print. We'll say captured first and second image for analysis. Okay, and that'll tell the user, okay, we did something there and we've moved on. So let's go ahead and Control X for me, hit yes, save that file, and we'll just page up and we'll go ahead and run that script. So we enter our while loop. It's now using Raspistill to record those images. It's pausing for a second and then it's moving on. So let's go ahead and break out of this with a Control C. And now if I go back to my FTP client, if I look in the folder here, I'll see I have a test 0 and a test 1. I also have the test pick. That was kind of that original alignment image just as a sanity check. And of course I could do the same thing in the on the command line here, right? Just with an ls. Let's go ahead and use Raspberry Pi's functionality to open those and just make sure that those look good. So we'll xdg-open. This will be test0.jpg. There it is. There is our first image. That's great. And hit the up button. Let's just compare with test 1. And that one looks good as well. Obviously, not much happened here in the last 1 second. Someone or something did not enter the user-defined area in front of my house, but we've confirmed the functionality of this part of our detection algorithm. Let's go ahead and clear the screen. Continuing on, we'll go ahead and open up the script again. Let's page down. We'll get to the end here. Now what we want to do is pass those images through this mask image function, right? So let's go ahead and mask images, and we'll say for this purpose we'll do test1 and test2. You can call it whatever you like. Let's go ahead and we'll cv2.imRead. We'll read in those images that were recorded by Raspberry Still, and we'll go ahead and read in test2. That'll be cv2.imRead of test1. Okay, so there's our first and second image. And then we'll punch those through the mask image algorithm, right? And if you recall, I had updated at the beginning of this lecture, lecture 2, I'd updated this function to return both the masked image, so the bitwise and result, and the gray image, right? So the gray is actually resized, converted from BGR to grayscale and blurred, right? So we can go ahead and call masked 1, and we'll call it gray 1. That'll be equal to mask image, and we'll pass that test1. And then we'll do the same thing here. Mask 2, comma gray 2 equal to mask image of test2, right? And that'll be both of those images that we recorded with Raspberry Still now passed through that function. And let's go ahead and write those to file so that we can take a look at them as well and just sort of sanity check the performance of this algorithm. So we'll say write images. Let's go with write masked images to file. Okay, so we'll begin with a cv2.imWrite, and let's go ahead and call this gray1.jpg. We'll write gray1 to file, right? Gray1 in this sense is effectively a matrix that defines an image. We'll go ahead and write that to file. Let's do the same thing, cv2.imWrite. We'll call this gray2.jpg. And let's do the same thing with the mask files as well, cv2.imWrite. We'll call this masked 1.jpg. Call this masked 1. And then let's write cv2.imWrite masked 2.jpg and write mask2 to file. So let's go ahead and save that file and run that script. Okay, so we'll just let it run once through the script here, and let's take a look at some of the files. So let's clean that up, clear, and let's run an ls. And there we have it, right? Here is our original script. Here's that alignment pick that we took, alignment image, test pick.jpg. So each time through the script then, it's recording test0, test1, and then each subsequent time through the loop, it's going to overwrite those. And that kind of helps in terms of disk space on the Pi. We also then pass test0 and test1 through the mask image function and write those to files. So we have gray1, gray2, mask1, and mask2. And let's just go ahead and sort of sanity check. Let's exeg.open gray1.jpg. There it is, right? Remember, it's grayscaled, it's resized, and it's blurred. That helps with computation time for the change detection. And let's also just make sure then that the masked images look good. And that looks good, right? If you recall in lecture 1, we went through and we dynamically defined the vertices of these points, and then we went ahead and cv2.bitwise and masked that file to create that mask. So we have a nice view of the front of the house. Here's kind of the front step, front stoop, and then a couple steps leading up to the house. So that all looks good. Let's go back into our script and continue. I'll page down here. Let's go down to the end and let's continue. So now we want to actually compare the two images and say, hey, has anything changed, right? So we'll compare the two images. And in this sense, we're going to define a threshold that says, okay, if enough pixels have changed by this amount. That's what we have to decide. Go ahead and kick off a video recording to notify, to send to the user, and then create the notifications to notify the user as well. So let's start with a initial pixel threshold. We'll just call it 50 pixels. Remember, we're comparing now two grayscale images, gray 1 and gray 2. And so the idea is each pixel is 8 bits, so it'd be 0 to 255. The question is, has the pixel changed by at least a value of 50, right? That would be sort of a substantial level of change. But could be tricked in a sense, right? You could imagine a nighttime scene, you may want to reduce that threshold. So there's certainly some elegant ways of doing this, and we're going to kind of give it a first cut here in a relatively straightforward fashion. I'll go ahead and define this detector total. I'll just kind of initialize this as a unsigned integer here. I'm going to initialize it as 0 just as sort of out of habit, and then I'll go ahead and redefine this detector total here in a second. I'll also create a detector array. This will be an array of zeros, right? And we'll give it a size here. We'll just use gray 2, that's fine. The shape 0, comma, gray 2 shape of 1. And then the data type here will be unsigned integers as well. Okay, and so detector, let's add in a couple letters here, detector, right, is initially a array of 0. So an n by n by 1 array where each value is currently 0. What we'll do then is we'll go through pixel by pixel and compare, pixel by pixel comparison, and we'll say, okay, if gray 1 to gray 2 has changed by a certain amount, go ahead and set that detector pixel value high, right? And so we'll just kind of go through and compare the two images and then switch the detector pixel accordingly. And then at the end we can say, okay, if we have enough detector pixels that have gone from 0 to 1, or in this case 0 to 255, then go ahead, there's been a change, something's entered the user-defined area, and initiate the recording. So for that pixel by pixel comparison, we'll say for I in range, we'll go 0 to gray 2 dot shape of 0. Gray 2 and gray 1 should be the same shape, so you should be able to use either one there. And then for each of those, let's go in, so we'll say for j in range 0, comma, gray 2 dot shape of 1. Right, we basically want all columns and all rows, or all rows and all columns. Either way, we're just going to go pixel by pixel and compare. Okay, so let's say if the absolute value of the difference of the two pixels, so we'll just give it an integer value for now. So if the absolute value of the difference of the two pixels, so this will be gray 2 of I comma j minus gray 1 of I comma j. If the difference between those pixels is greater than that pixel threshold, say, okay, that indicates some level of change, right? And so if that's the case, go ahead and set this corresponding detector array element, set that equal to 255, right? It's kind of like saying set it equal to 1 or high, low or high. And that says, okay, detector array will basically map out the change detection, the difference between gray 2 and gray 1. And if that change is above a certain level, so we've set the threshold here at 50 pixels, go ahead and set that detector element equal to 255, set that high. We then want to come down here, and now we want to sum the detector array, and that will now enable us to say, okay, did we have enough pixels change to indicate that someone or something has entered the user-defined area, right? So we'll say detector total, and I'll just again initialize this. We'll say numpy unsigned int. We'll give it 64 bits. Why not? And we'll say that'll be np sum of detector. Okay, so we'll take that full sum. Obviously, if image sizes grow, you'd want a larger and larger number here. So I just make it a nice big 64-bit unsigned integer. And then let's print that to the screen, right? So let's say print detector total equals, and we'll go ahead and just print detector total to the screen. I'll give myself a space here just for aesthetics. Okay. And let's go ahead and run that script. Let's make sure that the steps that we've coded up here are all functioning as intended. So we'll save that page up. Let's go ahead and run that script. Looks like we have a syntax error here. I have forgotten to include the bounding quotes. So we'll go back in, we'll edit that, no problem. Page down and see where we define that, right? This is that detector equals np zeros, no problem. Let's put in that second set of quotes, and we'll just make sure that I went ahead, didn't have the same error somewhere else. Okay, Control X save. We'll go ahead and clear to make this look a little bit better, and let's run that script. One too many things there. And we see here we have another error. Let's go back in and edit that value. I have defined that as pixel threshold. Here I only typed pixel thresh. So let's go ahead and redefine this. Instead of pixel thresh, let's call it pixel threshold. Get out, save it, and run it. And you see then each time through the loop, we're capturing a first and second image for analysis, and we're comparing the detector total value. So we're going to have this threshold that is values pixel to pixel changing, and this is prone to happen, right? If you're taking two pictures right after each other, you can have issues such as saturation between one image and the next. The camera's not warmed up between one image or the next, right? So there are some reasons behind such a change. And so because of this, we're going to set another threshold now, right? The first threshold, this pixel threshold, says, does each pixel change by at least a value of 50? We could tune that. Then the next one's going to be, okay, do we have enough pixels that have changed by this value? If so, something has entered the user-defined area. Okay, so the next step will be to Control-C out of here, go back in, and we'll edit this script, and now we'll add our next threshold to the script. Let's page down to the end of our script here. And actually, we'll leave the time.sleep in there for the moment. We'll remove that here at the end. Let's say if detector total is greater, so say detector total, which we were printing to the screen, printing to the window, or the terminal rather, if that's greater than some value, now I'm going to go ahead and call this 30,000 for the time being. Just like the pixel threshold, this detector total threshold will need to be tuned depending on the application. But we're going to take a first sort of cut at this process here in this lecture. If that happens, let's go ahead and tell the user, okay, so we'll say smart doorbell has detected someone or something at the door, right? That was the whole intent of the smart doorbell to begin with, right? So something has entered the user-defined area that defines that area in front of the door to our house, door to our apartment, wherever you may be residing. So if that happens, okay, very good. We've notified the user through the terminal. Let's continue now and go ahead and initiate that recording, right? So we'll come back in here and let's define a unique name for the new video file, right? You can imagine if you're leaving this smart doorbell running for days or weeks or a month at a time, you wouldn't want to record just one file and have it rewritten each time. Each time you recorded a new video file, you'd want to save that. And so we're going to give that a unique identifier via a unique timestamp, right? So we'll call this time string. And that'll be time. We'll call from the time package. Say time.string, time, string f time. And let's just go ahead and call this doorbell dash, and we'll give it the full timestamp, right? So the %y, %m for month, y for year, m for month, %d for day. Let's give it another dash, %h for hour, capital M for minute, capital S for second. Okay, that'll be our unique timestamp for that particular file. And then once we've created the timestamp, let's go ahead and now I'll call it, we had command before, we'll say command 2, that'll be fine, right? Let's go ahead and record a video. So we'll do a raspy vid in this case, give it a time. You know, you can decide on how long you want to record these videos. For this particular purpose, I'll just do a 15-second or 15,000 millisecond long video. I'll record at the same dimensions, so a -w for width of 1280, height, h for height of 720. We'll vertical flip it, we'll horizontal flip it. And we're going to give it another flag here, the frames per second. I'm going to record that file at 30 frames per second, and then I'll convert it here using MP4 box at 30 frames per second as well. So we'll -O for open, and then a space, and then let's add in now that time string value. And then we'll add to that page over here and make that look nice for those following along. And then we'll give it the .h264 at the end, right? So Raspy Vid natively records in the .h264 format. We'll convert that to MP4 here in a minute using MP4 box, right? So we'll go back, we'll use the os.system command again, and we'll run command 2. And then once we've finished with that recording, let's go ahead and notify the user again. So we'll just go to the terminal window for now, and we'll say finish recording, converting to MP4. And let's give it now a, let's call this, how about command 3? And we'll run this command 3. So we're going to use MP4 box. We'll give it a -FPS frames per second of 30 frames per second, right? We'll add in this file. So we'll say plus time string, right? It's a unique identifier that is the time. Of course, this is going to be doorbell. And then the full timestamp from year all the way down to second. So let's continue. We'll go plus .h264. So that'll say add in that .h264 file, and the output then would be the same name. So time string plus, and then this would be an MP4 file, would be the resulting file there. So we'll record in H264. Once we're done recording, let's go ahead and convert that then over to MP4, right? And so once we've done that, we have to go ahead and say, okay, os.system command 3, go ahead and run that command. And then once we're done with the conversion, let's go ahead and let the user know that we are finished as well. So we'll say finished converting file available for viewing. Now, if we take a look at some of our code, let's page up a bit here. We've got this time.sleep. You know, we really want to try and run this script as fast as we can, right? We want to look at 2 images for change detection, and then we want to get right back to it. So let's get rid of that time.sleep. This should be about the fastest we can do. For the moment, just for the moment, let's comment out. Actually, let's move these lines back, right? It's going to take some time to write all these files. And so let's only do that if we've actually detected someone at the door. So for a PC here, I'll just Control K to cut everything out of here. And I'll move that down to the end. I'll say if, you know, we went through and detected someone and we created a video, if that's the case, I'll hit Control U to paste it here. If that's the case, go ahead and write that to file. So we'll say, get those all tabbed over. And of course, we're in an if statement now, right? So we need an else as a result. If we have enough change, go ahead and do this stuff, but else we want to do something else, right? So let's take a look at that. Else, if nothing has been detected, we'll just tell the user that, right? Hey, nothing detected. We'll just say yet, right? Something's coming, okay? And so let's go ahead and save that and run this script, see if there's any errors, and let's take a look. Okay, looks like we have an error here. It looks like I forgot an E there. So let's go back in and take a peek. Okay, go back down, find my time string. Command 2 looks good. There's an E there. Looks like I forgot it here in Command 3. Okay, so we're in Command 3. Got a time, and an E here. All right, and got an E there. That all looks good. Okay, and we'll go ahead and run this script again. Okay, so I got the E there. And let's go ahead and just take a quick peek at our other commands. And actually, it looks like in Command 2, I need a space here, right? So that'll be a -F-H, okay, for the horizontal flip and vertical flip. And I'll just take a peek system here, -FPS and O, okay. So let's go ahead and save it. And clear the screen so we can see what's going on here. We don't want to edit it again. We want to go ahead and run it again. Okay, so look, we've encountered someone at the door, right? Or so the script would have us believe, right? So let's run this script through. It's going to go ahead and create a 15-second recording, and then let's take a look at the results. I'll also take a look at Command 3. Let's see, the MP4 looks good. Time string. Oh, I need a space here. I need a space between this .h264 and the file name. Time string looks good. And then the cv2.im rights look good. So let's go ahead, exit out of that. Let's clear this guy and let's run this script again. Okay, it looks like we've actually identified someone at the door. That's great. Someone or something at the door. So we're currently recording then our 15-second long video using Raspi Vid, and then we will convert that to MP4 using MP4 Box. Okay, so each time through the loop then, it looks like we're detecting someone at the door. That's probably not the case. That would be my guess, right? So let's get out of here. Okay, and you'll notice then the change, the detector total is quite significant here, right? It looks like 147,000, looks like almost 1.5 million, right? That's quite a large value. So let's go ahead and take a look at why that might be the case and what we can do about that. Let's go back in and take a look at that script, right? So we have our mask function, we have our while true, we're taking our images, we're comparing each time. Now, if we take a look at our detection algorithm in a little more detail, right? We set that pixel threshold equal to 50. We went through and defined this detector total and then this blank array, right? An array of zeros. Here's really where the meat of the comparison comes into play, right? For I in range 0 to gray 2, for I in range 0 to gray 2, so shape of 0, shape of 1. Then I have this absolute value of the integer difference between the two. Now, watch what happens if I take the absolute value of the integer difference of each respective element. So let's define that as an absolute value of the integer difference of int gray 2, and let's go ahead back in and now an int of gray 1. That should help us out. So let's Control X, save, and let's run that script again. And now look at the result, right? Detector total equals 0. Detector total equals 0. And so what we see here is what we often see when we're working in the Python world, right? Is we basically got bit by a data type issue, okay? So the way I set that up initially was take the value in each matrix, subtract them, and give me an integer result, Okay, but what we really wanted to do was tell Python explicitly, give me an integer value that is that matrix element, give me an integer value that is a matrix element of gray 1 and gray 2, and then subtract the 2 and give me the absolute value. So now there's nothing in front of my door. I can attest to that. And our detector total is equal to 0. So let's clear this file and let's go ahead and actually test this out. Okay, so I'm outside of the house right now. Let's go ahead and test the functionality of this script. I'm walking from the street. I'm now approaching the door. And let's take a look and see if this functions as intended. Oh, looks like Smart Doorbell has detected someone or something at the door. I suspect now it's going to begin to record a 15-second long video, and that'll give us a good idea of the functionality of this initial section of the script. I'm back at the house now. Let's go ahead and take a look at the files that were created by this initial test. Okay, so here is our first image and second image. Now, you'll notice there's nothing happening between these two images because in the time it took to get back inside the house, the script has continued to run. So I'm actually inside the house, so you won't see any change on those images. However, if I look at masked 1 and masked 2, you'll notice here are the two images that were recorded as I was approaching the door, right? So that's me entering the user-defined area, and there has been enough change now to indicate that someone or something has entered that area, right? So if I look at the grayscale images, you'll see then there are the images that we're actually using to analyze to determine if someone or something has entered the user-defined area. And again, we shrink down those masked images to reduce the processing time to determine if someone or something has entered that area. Let's take a look at the video. Here I am then, right? I've initialized a recording session because my presence has met that detection threshold, and a 15-second long video of me being recorded has been generated. So let's recap then what we've accomplished in lecture 2 of this lecture series. We've taken the code developed in lecture 1 that allowed us to mask an image, and now we've added the looping ability to compare a first and second image, right? And we've defined now some detection criteria beyond which we could say, okay, go ahead and record a video, notify the user that someone or something has entered that user-defined area. So each time we're recording an image, a first and second image, we're masking it, we're grayscaling it, we're blurring it, and then we're comparing the two images to decide, okay, has there been sufficient change such that someone or something has entered that user-defined area? And if so, go ahead and create a video file that will ultimately upload to the user, and then we'll notify the user through email and through text message that, hey, someone or something has entered that area. So that wraps up the material for lecture 2 of this lecture series. In lecture 3, we'll continue with development of our algorithm, and we'll add in an Internet of Things approach such that when the detection algorithm has been initiated, once it's complete, we'll notify the user and deliver these data products to the user. Thanks a lot. If any questions, as always, reach out anytime. I look forward to seeing you in the next lecture.